All right, so let's talk about behavior of graphs today. So when this says f of x equals x, that's just a fancy way of saying y equals x. Y equals x squared, y equals 0, y equals the absolute value of x. It's just saying the function of x. Yes. All right, so let's get a sense of behavior of graphs. So I heard a question earlier about how would you know if we just draw the line. When I'm talking about behavior of graphs, we really are talking about behavior. It's not going to be to scale. Okay, I'm going to do a few of them to scale, but what I really want you to get out of this lesson is what it's supposed to look like. So, y equals x, we already talked about that, right? This actually has a y-intercept of 0, so I would start at the origin, and a slope, that's the b, yes, the y-intercept, and a slope of 1. So I would go up 1 over 1, up 1 over 1, up 1 over 1. That graph would look like this. Right? That's that identity graph. And yes, that's that identity function. Every time x is 1, y is 1. When x is 2, y is 2. When x is 3, y is 3. All right, let's talk about the next one. What does x squared look like? The function of x squared. Better? It looks like a U, right? It's a parabola. The parent graph is a parabola. If I were to substitute 0 in for x, wouldn't I get 0? 0 squared is 0. And if I were to substitute 1 in, 1 squared is 1, so 1, 1. If I were to substitute in negative 1, I would also get 1, because negative 1 times negative 1 is a positive 1. What if I were to substitute in 2? I would get 4, because 2 squared is 4, right? So what happens if I plug in or substitute in negative 2? Wouldn't I also get 4? Not negative 4. Negative 2 times negative 2 is positive 4. Remember this from Algebra 1? It's a parabola.
I remember the shape and not how you got.
Okay. Well, don't worry about the plotting and using the tables yet. I'm going to do that in the actual lesson. This is just about the behavior of it. Okay? Let's do this one. The function of x equals 0, y equals 0. That's that constant function. So what would that one look like? Y equals 0 would be a constant horizontal line at 0. And the absolute value function we talked about looked like a v, correct? Let's plug in values and see. If x is 0, y is 0. If x is 1, what's the absolute value of 1?
1.
1. What's the absolute value of negative 1?
1.
What's the absolute value of 2?
0.
What's the absolute value of negative 2? See how it makes a v like that?
Yeah. So, the only parabola is x squared minus
No. It's only a parabola if it's x is squared. This is a parabola. This is an absolute value function. See how x isn't squared here? It's just x inside of an absolute value sign. It's not going to look like a parabola. You know why? Because it's going to be a straight line with a V. It looks just like this one, only this part's cut off and put in this positive direction. I didn't take roll. Yes, sir. Yes, please. Yes, please. I'm glad you're on it. Okay, Jesus, take a look at this. No. Savannah. Okay, so see how this one, if I have the difference between this parent graph and this paragraph is that if I plug in or substitute in a negative value, it will never go negative. It will always go positive. See that? So it's like taking this and flipping it up this way. Right? Because if I were to substitute in any value, -3, if I'm going -3, absolute value of -3 is always going to be positive. Okay? It's going to make more sense as I keep going. All right. So these are on my parent graph. Y equals x. You need to get rid of that guy. Y equals x looks like this. Right? That's an identity function. Every time I substitute one value in for x, I'm going to get the exact same value out for y. This is a parabola, right? Or a quadratic function. This is a constant function. A good way to explain a constant function is like cell phone. A cell phone bill that has, a cell phone plan that has a constant value of minutes. What would we call that? An unlimited plan, right? So let's say it's $30 a month. We'll say this is 30 right here. So if you talk for 0 minutes, you pay $30. If you talk for 10 minutes, you pay $30. If you talk for 100 minutes, you pay $30. That would be a constant function, right? Okay. And this is an absolute value function. Now let's play with each one of these. I am going to use my orange for the top ones. Then I'm going to move to blue. I need a darker blue. And then I'm going to move to green. So please feel free to color code yours as well with those colored pencils. I passed them out. You see some? You can use highlighters. You can use whatever you want. I just provided the colored pencils just for you.
What are we coloring?
It's your notes. Graphs. We're going to compare graphs. All right, so let's start with this function right here, x plus 2. You guys can easily graph x plus 2. We always begin with the y-intercept, right? So if the y-intercept is 2, I'm going to go up 2 on the notes that I provided for you. So I begin at 2. I'm going to rise up 1 over 1, right? Because the slope is 1. So up 1 over 1. Up 1 over 1. What do you see? How does y equals x compare to y equals x plus 2?
Parallel.
Good job. It's parallel. So couldn't I just take this line, copy it, paste it, change the color of it, and shift it up 2? Isn't that all that's happening to that line? It's just shifting up 2. Right? Let's look at the next one. Actually, I'm going to leave that there. Let's move on. Yeah. No. Say it again.
On the yellow, on the orange one?
Yes. We started at 2 because we start at 2, right? So I went up 2. And then my slope is 1, right? So I went up 1 over 1, up 1 over 1, up 1 over 1. And since my slope is the same as this one, I know that I'm going to have the same slope. These two lines are parallel. So I'm trying to show you that the only thing that changes between this right here and this right here is a shift up 2. You see that? That's the only thing between this line and this line. They are the same, only it's shifted up 2. Let's look at this one. So what do you think is going to happen with x squared plus 2? It's going to start at 2, and it's going to have the exact same shape. And I'm going to prove it to you right now. If I substitute 1 in for x, 1 times 1 is 1. 1 plus 2 is 3, right? So 1, 3. Isn't this one the one I did in black? It's just one away, just like that, right? Looks just like it. What if I substitute in -1? -1 times -1 is 1. 1 plus 2 is 3. So if I go in the negative direction one, I'm still going to get 3. Just like the black one, just shifted up. So what if I were to substitute in 2? 2 squared is 4. 4 plus 2 is 6. If I plug in 2, I get 6. Guess what's going to happen if I substitute -2? I'm going to get 6. So my graph looks exactly the same, just shifted up 2. Let's look at our constant function. What do you think happens when I say f of x equals 2?
The one is up.
It's going to shift up 2. See how, are you figuring it out?
Yeah.
What do you think is going to happen to the absolute value function?
It's up to.
It's going to shift up 2. It's going to start at 2, and it's going to look exactly the same. Let's talk about our blue graphs now. This function says 4x minus 1. Now, just so you guys understand, we all should be able to graph this, right? So let's graph it together, and then I'll talk about the behaviors of the rest of them. So I begin at -1, because that's my y-intercept. So I'm going to plot a point at -1. My slope is 4. So I'm going to rise 4, 1, 2, 3, 4, and I'm going to run 1. I'm going to graph that line. How does that line compare to the black line, the parent graph? It's not perpendicular, but it's intersecting with it. But look at the steepness. This one was parallel. This one is now a lot more steep than that one. It's not perpendicular. The only way it would be perpendicular if it was -1. Good job. Good job. Let's graph this last green one so then we can really talk about what's going on here. So the green one, I start at -6. 1, 2, 3, 4, 5, right about here. And my slope is now 1/2. So I'm going to rise up 1 and run 2. How does this line compare to the parent graph? It's not as steep, right? This one's super steep. This one's not as steep. What do you think's happening?
How did you graph it from 1/2?
I started at my slope intercept, and I went up 1, rise 1,
Oh.
run 2. So what's happening? This black one here is the parent graph. That's a regular y equals x. But as soon as I make a constant, first of all, we've learned that if I add 2, it shifts up. If I subtract 1, it shifts down. If I subtract 6, it shifts down 6. But what's going on with this constant? As soon as I put a number in front of x, it's either getting really steep or it's falling not so steep. Yes?
Well, when you have x is higher than y, it goes up higher and only goes so far for y, which we make steeper. And then for the other one, I mean, you have 1/2, so if you only go up 1 and over 2, it's going to get, I don't know the word for that.
Less and less steep, right?
Yeah.
You know, the way I like to look at it is also, if you look at a number line, if you're at 0, let's say this is 0, and I'm going to show you a YouTube video tomorrow. Let's say this is 1, and let's say this is, we'll just say 2. As you're going away from 0, right, you're going further and further and further away from 0. This line's getting steeper and steeper and steeper, right? Isn't it going further away from 0 if I were to measure it like this? It's going further and further. I'll even take this line and adjust it. This is at 0. Here's at 1 over 1 with a slope of 1. As my slope gets larger and larger, greater than 1, greater than 1, greater than 1, it gets steeper and steeper and steeper. Here's back at 1 over 1. Here is 1/2. So what do you think it's going to look like if it's at 1/4? And 1/8? And 1/16? And 1/32? Only it would be, you know, up here. It's going to go further and further down to 0. Isn't that what happens on a number line? As I go 1/2 is closer to 0, 1/4, 1/8, right? It's going closer and closer and closer to 0. I'm going to show you something where on YouTube tomorrow that's an actual video of somebody making the lines move like that. It's pretty cool. All right, let me put my line back where it's supposed to be. It's supposed to be right there, and let's talk about this one over here. So what do you think is going to happen with 4x squared minus 1? This is not going to be to scale. I can't emphasize that enough. We are going to talk about what it looks like. What's going to happen to its vertex? The vertex went up 2 when I added 2. It's going to go down 1. What's going to happen to the shape of the parabola? What do you think? It's going to get thinner. Because as I put in a value, well, I'm just going to graph this one. Let's say x is 2. Let's say x is 1. 1 squared is 1. 1 times 4, that just made it bigger. I multiplied it by 4. So that's 4. 4 minus 1 is 3. So if I plug in 1, I would get 3. If I plug in -1, I would get 3. This is a very skinny graph. Let's do this green one. I would start down at -6. And I'm just guessing here. I'm guessing it's going to be something like this. So I'll plot it for you. 1, I'm going to put in 2, because I want to get rid of that 2 in the denominator. 2 squared is 4. What's 4 divided by 2? 2. What's 2 minus 6? -4. So if I were to substitute in 2, I would get -4. I was a little bit off. But my point is, if I asked for this on a test, if I asked for the behavior, and I asked for the behavior of 1/2 x squared, I would expect a wide line like that. That would tell me that you know what I'm talking about. If I asked for something, let's look here. If I gave you a problem and said, if the parent graph looks like this, what does 1/4 x squared plus 2 look like? I would be up 2, right? And it would be really wide. That would tell me you know what you're talking about. It's a wide graph, and it's shifted up 1. Now, if I tell you to graph it, then it needs to be precise. But when I want the behavior means what is it supposed to look like in theory? All right. Let's move on. What do you think this one looks like? These are going to be easier, right? What's this one going to look like? It's going to be shifted down 1. And the green one? Shifted down 6. I think this is 6 right here. That's the simple one. You know what? This one's pretty simple too. What's going to happen to this one? And I am not going to do this to scale, because that's the problems we're going to do next, is we are going to do the absolute value function to scale. So don't worry about that part of it, okay? So let's just make this rough sketch. What is the absolute value of 4x minus 1 going to look like? Where am I going to begin? Where's my vertex going to be? At -1, and it's going to be kind of steeper than the parent graph. And what about 1/2 of x, the absolute value of 1/2 of x minus 6? Where's that going to begin? Down 6 and wider. Starting to get it? Making some sense? How things are shifting? This is the black one, is your normal function. The function of x when the absolute value of x, right? Or y equals the absolute value of x. That's the black line, right? The orange line is the same thing. It looks exactly the same, right? Only I added 2. So when I add 2, see how the black one shifted up to the orange one? It's just up 2. Then when I did this one, the blue one, it shifted down 1, but since it has a coefficient of 4, it got skinny.
So whenever a number,
These numbers have an effect on what the graph looks like. This is your baseline right here. This is what all graphs look like. Then as soon as I do this, that means the graph is shifted up 1. It looks exactly the same, only it's moved up. See that? Can you see it?
yeah,
And then when let's say I would just say the graph is, I'm going to call it the function of absolute value of x minus 10. That's this same graph, only down 10.
I guess I just don't get how.
It goes skinny and gets fatter.
I don't get that.
Okay. So if I were to actually, let me move this back up. That's not right. Oh, I moved this whole thing. Yikes. We're okay with that, right? Okay. I'm going to plot some points for you because this is really important for you to understand. So let's look at the skinnier one, the 4x minus 1. Okay. If I were to substitute x in, let's make x 1. So 4 times 1 minus 1. 4 times 1 is 4 minus 1. The absolute value of 4 is 4 minus 1, which is 3. So my point would be 1, 3, right? I go over 1, up 3. If I were to just plug it in for 1, it would be 1, 1, right? The regular graph, this one right here. But when I do it here, I should have been using blue. When I'm doing this one, it's getting skinnier. Let's look at this one. I'll do the green one. If I were to substitute in 2, f of 2, that would be the absolute value of 1/2 times 2 minus 6. 1/2 of 2 is just 1, right? Minus 6 equals -5. So over 1, -1, 2, 3, 4, 5. Maybe it's because I'm putting both of this together with this. Let's work on the ones we're going to do now because I'm going to plot every single one that we do next. This is more about what's happening. Do you understand why this one gets skinnier? And this one gets wider? Do you understand how this one gets steeper? Okay. It's the same thing. If the constant, if the number in front, or the constant in front of that variable, the larger that number gets, the steeper that graph is going to go. And if I have a steep on one side and a steep on that side, that makes them both steep, that makes them really narrow. Right? Okay, let's move on. Special functions. So this page, now these are to scale. The last one I was doing wasn't as much to scale, these are to scale. So you have those for your reference. Now let's use them. Pencils down. I'm going to show you how to do this. All right. Exactly. I don't want you to have it because I want you to just pay attention right now. All right. Thank you. So the easiest number to substitute in for x is always 0 when you're graphing, correct?
Right.
So I'm going to substitute in 0. The absolute value of 0 plus 1 equals the absolute value of 1, which is 1. So I would graph 0, 1. Next easiest number would be 1. So the absolute value of 1 plus 1 is the absolute value of 2, which is 2. 1, 2. Starting to go in a straight line, right? Let's try negative 1 and see what happens. If I substitute in negative 1 plus 1, I get 0. Negative 1, 0. We've got a V shape, right? I want to see if it's going to keep going down or if it's going to start going up. So let's substitute in negative 2. Negative 2. Negative 2 plus 1, the absolute value is negative 1, which is 1. So if I substitute in negative 2, I get 1. I start to see a V, right? So now I need to confirm it. I'm going to pick one more point. What would you pick? Negative 3. I want to plot negative 3 because I'm going to see if it's symmetrical right there, right? So if I substitute in negative 3 plus 1, I get, negative 2. Negative 2, which is 2. If I substitute negative 3, I get positive 2, and I have my absolute value function. Oops, I need this one. Looks like this. Okay? My steps. Table, graph the points, be really cognitive of your symmetry, looking for symmetry. That way you don't have to plot a bunch of points. Less is more, right? Once you start seeing some type of symmetry, use that symmetry. Domain and range. Let's talk about domain and range. The domain values. I'm going to move over to the board. The domain values. The way I test it is, if I plug in a value for x, I'm plugging in a value for x, am I going to get an output of y? So if I plug in 1, will I get a y value? Yes. I'll get 2. If I plug in 4, am I going to get a y value? Yes. It's about what? It's probably not, but we're just going by the graph. If I put in 1,000,000, what do you think? Yes, right? Let's go in the negative direction for x. If I go to negative 1, do I have a y value? Yes. If I go to negative 2, do I have a y value? If I go to negative 3, do I have a y value? All the way this way. So no matter what I plug in or substitute in for x, I will always have a y value. All real numbers. No matter what, if I plug in, no matter what x you can think of, I'm going to get another number, right? Let's talk about our y value. If I plug in, these look a little different. If I plug in 1 for y, am I going to get an x value? This one's 0, right? If I plug in 2 for y, am I going to get an x value? I'm going to get 2. I'm going to get 1. And I'm also going to get, oops, not negative 1, but negative, what's that, 3? It's getting messy. I don't like messy. Let's do another one. If I plug in 6 for y, if 6 is y, do I have an x value? I have one here on the positive side, and I have one here on the negative side, correct? Let's go in the opposite direction. What if y was negative 1? Am I ever going to get an x value? Down here, ever going to get an x value? Ever have an ordered pair? Never going to have an ordered pair with negative 3, never going to have an ordered pair with negative 4, never going to have an ordered pair with negative 6, forever down here, right? The only numbers, the only points or ordered pairs I will get for values of y is if y I just almost stole my gun. I got really excited. And y is greater than 0. That helps? So the range of this function is all the numbers of y such that y has to be greater than or equal to 0. Is that making a little more sense now? If you can produce an ordered pair from it, it is part of that function. If you can't, if I put any value in for negative y, I'm never going to have an ordered pair anywhere out here in this space, right? This space will never have an ordered pair. Okay, let's go then. Exactly. You have to put it's greater than or equal to 0 because there is a point that's got where y is 0. All right, I'm going to do another one here. Actually, let's look at the behavior of this. I'm going to skip over that. This is what I really want to hone in on, guys. Check this out. What happened to this graph compared to a parent graph? It shifted in the direction to the left, over 1. When we talked about absolute value, didn't we say it's the difference between x and see that? No. Absolute value. The difference between x and negative 1 is 1. Right? When you're talking about x absolute value, isn't it always about the difference between two things? The difference between this number and this number equals something else. So the difference between x and negative 1 would be 1 in this instance for this point right here. That being said, what would this one look like? I'm not going to do this one because I'm running out of time. How would that one shift? It would be over here, right? Because the difference between x and 2, and it would look like this, right? Because it doesn't have anything in front of the x. It's not shifted up or down. It's just over 2. So I want you to do these two with me in the next couple minutes. These are on your paper. What's this one going to look like? Shifted to the right 3. What's this one going to look like? Shifted over to the left 2. Let's plug in some values. 0 is the easiest one, right? 0 minus 3 is negative 3, which the absolute value of negative 3 is just 3. So 0, 3. I said it's going to be shifted over 3. Let's plot that point and see if we're right. What if we plug in 3? What happens? 3 minus 3 is 0. Am I right? If I'm really right, I should be able to plot one more point and see symmetry. Nope, not negative 3. How about 6? Let's put in 6. What happens? 6 minus 3 is 3. Does it work?
Yeah.
Yep. That's not that bad. You understand it now, don't you? How it's supposed to, you see what I mean by it? It really helps you if you understand the behavior of the graph. Then you know where you're supposed to be going, and you just plug the values in and see if you're right. What about this one? I'm going to do this one in a different color. So the easiest one would be plug in 0. 0 plus 2 is 2. 0, 2. There's my first point. Where did I think this one's going to shift? To the right or to the left?
Right.
To the left. Where do I think it's going to land? I think it's going to land right there. Let's put it in and see. Negative 2. Negative 2 plus 2 is 0. Am I right? What's the next number I should test? Negative 4. Negative 4 plus 2 is negative 2, which is 2. If I plug in negative 4, I get 2. Remember the graph paper, okay, guys? We'll talk about our closing thought tomorrow. Good job.